Welcome to the Deep Dive. Today, we're going to be talking all about hydrogen.
Oh, yeah.
And might seem kind of basic at first,
Right.
but we've got a chemistry textbook with us,
Okay.
and also some really interesting notes and some scanned pages. So
Cool.
I think it's going to be a pretty interesting deep dive.
You're not wrong.
One of the things that really stuck out to me
Yeah.
was in the notes.
Okay.
He was talking about how hydrogen is kind of like a rogue element
Okay.
and how it doesn't really fit in on the periodic table.
That's one way to put it.
What do you mean by that?
Well, it's the first element, right?
Okay.
The smallest one.
Right.
And it kind of exists in this weird limbo.
Yeah.
Like it hangs out with the alkali metal sometimes.
Okay.
But then it also has this thing for halogens.
It can't make up its mind.
Right.
So is that why it's all alone at the top of the periodic
I
table?
think exactly.
Sure.
Even Dmitry Mendeleev.
The guy who made the periodic table.
Yeah. The guy who created the periodic table, he had a tough time figuring out where to put hydrogen.
Okay.
Because it can gain an electron like halogens do.
Right.
And it can also lose an electron like the alkali metals.
Yeah.
So in the end, he just gave it its own special spot.
The category of one.
Pretty much.
Okay, so that's interesting.
Yeah.
But how was hydrogen even discovered in the first place?
So back in 1766,
Okay.
there was this English scientist named Henry Cavendish.
Okay.
And he was doing some experiments with metals and acids.
Uh-huh.
And he stumbled upon this flammable gas.
Great.
He didn't know what it was at first.
Right.
But he knew that it was something new.
So he was like, huh, this is interesting.
Yeah, exactly.
Okay, so then what happened?
Well, then Antoine Lavoisier came along.
Okay.
You know him as the father of modern chemistry.
Right.
And he gave it the name that we all know and love, hydrogen.
Which means,
Water former.
oh, wow, that's cool.
Yeah.
Okay, so we've got this tiny atom
All right.
that's kind of got a rebellious streak.
Yeah.
And a history that's rooted in experimentation
Uh-huh.
and is a key component to life as we know it.
Yeah.
That's pretty amazing.
It is.
The notes also mention something called atomic hydrogen,
Okay.
which sounds a lot more intense.
Yeah.
What is that?
So atomic hydrogen is basically hydrogen in its purest,
Okay.
most reactive form.
Okay.
So imagine you have a hydrogen molecule, which is usually two hydrogen atoms bonded together,
Right.
and you split it apart.
Okay.
Now you have these lone hydrogen atoms that are
Right.
just desperate to bond with something,
Anything.
anything, to become stable again.
They're on a mission to find a partner.
Exactly.
Okay.
And because they're so reactive, atomic hydrogen can do some pretty amazing things.
Oh, really? Like what?
Well, for example, it can react with metals to create metal hydrides,
Okay.
which are used in all sorts of applications,
Interesting.
from batteries to fuel cells.
So even though it's unstable,
Yeah,
it's still incredibly useful.
that's
But how do scientists even create atomic hydrogen?
you're right. You're not going to find it just floating around in nature.
Right.
You need a lot of energy to create atomic hydrogen.
Okay.
And typically, this involves heating hydrogen gas to extremely high temperatures.
So we're talking serious heat here.
Yeah.
What does that actually do to the hydrogen molecules?
So the intense heat breaks the bonds between the hydrogen atoms,
Okay.
and this frees them up to become those highly reactive lone atoms.
Okay.
And this process actually absorbs energy.
Okay.
And scientists call that an endothermic reaction.
Endothermic.
Uh-huh.
So the heat's going into the reaction rather than being released?
Right.
I'm guessing this is not something I can do on my kitchen stove.
Definitely not.
Right.
You need specialized equipment and very controlled conditions to do that.
Okay.
Now, speaking of reactive hydrogen,
Yeah.
the notes also mention something called nascent hydrogen.
Mhm.
Have you heard of that?
Yeah, I was wondering what that is.
So it sounds very similar to
Mhm.
atomic hydrogen, but there is a subtle but important difference.
Okay.
Think of nascent hydrogen as atomic hydrogen that's freshly generated
Okay.
and hasn't had a chance to recombine yet.
Okay.
So it's like the newborn baby version of atomic hydrogen.
Even more reactive.
Even more reactive,
Eager to bond.
eager to bond, yeah.
So it's like atomic hydrogen on steroids.
You could say that.
Okay.
And because of this extreme reactivity,
Yeah.
nascent hydrogen is an incredibly powerful reducing agent.
Remind me what a reducing agent is.
So a reducing agent is basically a substance that donates electrons to another substance.
Okay.
And in chemistry, the transfer of electrons is a really big deal.
Okay.
It drives all sorts of reactions, including the reactions that produce energy.
So nascent hydrogen is like the ultimate electron giver.
Exactly.
All right. So how does that actually work in the real world?
Well, one of the classic examples is its reaction with potassium permanganate.
Okay.
So potassium permanganate is a powerful oxidizing agent. which means it likes to steal electrons from other substances.
Uh,
And when it's dissolved in water, it creates this really vibrant purple solution.
okay.
But when you introduce nascent hydrogen,
Yay.
it readily donates electrons to the permanganate ions.
Okay.
And this causes the solution to lose its color.
It changes colors.
It does.
That's wild.
It is. And it's not just potassium permanganate.
Hmm.
Nascent hydrogen can also reduce other colorful compounds,
Okay.
like potassium dichromate.
What does that do?
So it changes it from orange to green,
Wow.
and ferric chloride,
Okay.
which turns from this yellowish-brown solution to practically colorless.
So nascent hydrogen's like a magician making colors
This
vanish
is a great way to think about it.
with a flick of its atomic wand.
Exactly.
All right, so we've covered atomic hydrogen.
Yeah.
And it's even more reactive cousin nascent hydrogen.
Mm.
But I have a feeling there's more to the story.
Oh, there's always more to discover.
Yeah.
And in the case of hydrogen, it gets even more interesting when we consider its isotopes.
Isotopes.
Yeah.
Remind me what those are again.
So isotopes are like different versions of the same element.
Okay.
So they have the same number of protons,
Right.
which
Yeah.
defines the element,
Mm.
but they differ in the number of neutrons in their nucleus.
Okay.
This means that they have slightly different atomic masses.
So they're all hydrogen, but they come in different weights.
Yeah, that's a good way to put it.
Okay.
And in the case of hydrogen, there are three main isotopes:
Okay.
protium,
Okay.
deuterium,
Uh-huh.
and tritium.
Okay, so break those down for me.
All right.
Tell me about protium first.
So protium is the most common hydrogen isotope. It's the
Okay.
one we've been talking about so far.
Okay.
Just one proton and no neutrons in its nucleus.
So it's the basic model, the original hydrogen.
Right.
What about deuterium?
So deuterium is like protium's heavier sibling.
Okay.
It has one proton and one neutron,
Okay.
so it's still hydrogen. But it's about twice as heavy as protium.
Heavy hydrogen.
Heavy hydrogen, yeah.
Interesting. Okay, what about tritium?
Tritium is the largest of the three.
Okay.
It has one proton and two neutrons,
All right.
and it's also radioactive,
Okay.
which means it's unstable and decays over time.
But it still has application.
But it has some fascinating applications despite its radioactivity.
Okay, so we've got these three isotopes.
Yeah.
Protium, the common one, deuterium, the heavy one, and tritium, the radioactive one.
Right.
What
On-
makes them so special?
Well, each isotope has its own unique properties and applications,
okay.
which we'll delve into later, but I think this is a good place to stop for now.
Yeah, that was a lot of information.
We covered a lot of ground.
From hydrogen's rogue status on the periodic table to the world of atomic and nascent hydrogen, and then its isotopes.
We only just scratched the surface.
I can't wait to dive even deeper into this amazing element.
Me too.
So join us next time for part 2 of our hydrogen deep dive, where we'll explore the unique applications of hydrogen isotopes, delve into the intriguing world of heavy water, and uncover hydrogen's potential role in shaping a sustainable future.
See you then.
Welcome back to our deep dive into the world of hydrogen.
It's good to be back.
Last time we left off talking about hydrogen's isotopes, protium, deuterium, and tritium.
And you were about to ask what makes each isotope so special, right?
Yeah, I'm curious to know what they actually do
Okay.
and why anyone besides a chemist would care about these different flavors of hydrogen.
Well, for starters, let's consider protium.
Okay.
It's the most common hydrogen isotope.
Uh-huh.
And really, it's the workhorse of the hydrogen family.
So the basic building block, but what's its claim to fame?
Protium plays a vital role in a wide range of industrial processes,
Okay.
including the production of ammonia.
Ammonia. Okay.
You might not think about it much,
Okay.
but ammonia is a crucial ingredient in fertilizers,
Okay.
which are essential for modern agriculture.
So protium is indirectly helping to feed the world.
Absolutely.
That's a pretty big impact for the simplest element.
It is, and it's not just about fertilizers.
Okay.
Protium is also involved in the Haber-Bosch process.
Haber-Bosch.
Yeah.
Okay.
It's this groundbreaking industrial method for synthesizing ammonia on a massive scale.
Okay.
This process revolutionized agriculture in the 20th century,
Okay.
allowing us to produce enough food to support a growing global population.
So protium's quietly working behind the scenes
Yeah,
to make modern life possible.
pretty much.
That's amazing. What about deuterium, the heavy hydrogen? What's its specialty?
So deuterium is a bit more specialized,
Yeah.
but it has some incredibly important applications, particularly in the realm of nuclear science.
Nuclear science. Okay, so we're talking about serious stuff here.
We are.
What does deuterium actually do in nuclear science?
Well, one of its key roles is as a tracer in nuclear reactions.
Not tracer. Okay.
Scientists can use deuterium to track the movement of atoms during these really complex processes.
So it's like a little detective helping scientists follow the clues in the atomic world.
I like that analogy.
Okay.
It allows them to understand how atoms interact and behave during nuclear reactions,
Okay.
which is essential for both research and practical applications.
I see. And I remember you mentioned something about deuterium being involved in nuclear fusion.
You have good memory.
Nuclear fusion.
Yeah.
That's the process that powers the sun, right?
Yeah.
And I always heard that it holds immense potential as a clean and nearly limitless energy source for the future.
It does.
But how does deuterium fit into all of this?
Well, deuterium is one of the key ingredients in fusion reactions.
Okay.
It can fuse with another hydrogen isotope tritium to release enormous amounts of energy.
So it's like the fuel that could one day power our planet
Exactly.
in a sustainable way.
It's a long-term goal,
Right.
but scientists around the world are working tirelessly to make fusion power a reality.
And deuterium is a key player in those efforts.
It is.
This is amazing, this seemingly simple element. He's connected to the very processes that power stars.
Right.
And could potentially solve our energy crisis.
It's pretty remarkable.
It is. Okay, so what about tritium?
Yeah.
I know it's radioactive, which sounds a bit scary,
It does.
but I'm guessing it has some practical uses too.
You're right. Tritium is radioactive, but it's actually a very weak emitter.
Okay.
And it has a relatively short half-life.
Okay,
So despite its radioactivity, it has some really remarkable applications.
so it's not as dangerous as it sounds.
Right.
What kinds of things is tritium used for?
One of the most well-known applications is in self-luminous devices.
Self-luminous device.
Like exit signs watches
Okay.
and even some gun sights.
Wow,
These devices glow in the dark without needing any external power source.
that's pretty cool.
It is.
So even though it's radioactive,
Yeah,
it's being used to make things safer and easier to see in the dark?
exactly. And it's not just about glow-in-the-dark stuff.
Okay.
Tritium is also a valuable tool in biological research.
Biological research.
Scientists use it as a tracer to study metabolic processes.
What are those?
Those are the chemical reactions that occur in living organisms. So
Okay.
it's like a tiny beacon allowing scientists to track the movement of molecules within cells and organisms.
So kind of like deuterium,
Kind of like deuterium, yeah,
in a different way.
in a different context.
Okay, very cool. So we've gone from protium helping to feed the world
Right.
to deuterium potentially powering our future
Uh-huh.
and tritium illuminating the darkness
Yeah.
and unlocking the secrets of life.
It's amazing, isn't it?
That's incredible. Who knew hydrogen isotopes were so versatile?
And speaking of remarkable things,
Yeah.
there's another intriguing aspect of hydrogen we need to discuss: heavy water.
Heavy water. You've definitely piqued my curiosity.
Hello.
What exactly is heavy water?
Okay, so heavy water, or deuterium oxide as it's scientifically known,
Okay.
is water but with a twist.
Okay.
Instead of regular hydrogen atoms,
Uh-huh.
it contains deuterium.
The heavier hydrogen isotope we talked about earlier.
Exactly.
So it's like water's bulkier cousin.
You could say that.
Okay.
And this extra weight comes from that extra neutron in the deuterium nucleus.
Right.
And this difference in mass actually affects the properties of heavy water in some interesting ways.
Okay, how does heavy water behave differently from regular water?
Well, for starters, it boils at a slightly higher temperature than regular water,
Okay.
about 1 degree Celsius higher.
Okay.
And it also freezes at a slightly higher temperature.
So it's a bit more resistant to changes in temperature.
You could say that.
Does this difference in mass have any other noticeable effects?
It does. Heavy water is also denser than regular water.
How much denser?
About 10% denser, to be
10%.
precise.
Wow, so it really lives up to its name.
It does.
It's heavier in more ways than one,
Exactly.
but if it's basically just water with a heavier hydrogen,
Yeah.
why are we even talking about it?
Well, it has some practical applications.
Like what?
One of its most important applications is in nuclear reactors.
Nuclear reactors, so it's connected to the nuclear world.
It is.
Just like deuterium.
It is.
What role does it play in nuclear reactors?
Heavy water acts as both a coolant and a moderator in certain types of reactors.
Okay.
It helps to control the nuclear fission process,
Okay.
which is the splitting of atoms that releases energy.
So that sounds like a pretty important job,
It is.
given its connection to deuterium and the whole nuclear fusion thing we were talking about earlier.
Exactly. It's all interconnected
Yeah.
in this fascinating world of atomic science.
Okay.
But heavy water isn't just limited to nuclear application.
So what else is it used for?
It's also used in research,
Okay.
particularly in the study of metabolic processes.
Metabolic processes again.
Yeah, scientists can use heavy water to track the movement of molecules within biological systems.
So similar to how they use tritium.
Similar to how they use tritium, but in different contexts.
So it's like another tiny detective helping scientists unravel the mysteries of life.
That's a great way to put it.
This is all so fascinating.
It is.
My brain is starting to feel a bit overloaded.
I know we've covered a lot.
We've covered so much ground, from hydrogen's rebellious nature on the periodic table to the amazing properties of its isotopes
Yeah,
and the intriguing world of heavy water.
we have, but there's still one more fascinating aspect of hydrogen that we need to explore.
Okay, I'm all ears.
Yeah.
What else is there to discover about this incredible element?
Well, we've talked about hydrogen's potential as a clean energy source,
Uh-huh.
but we haven't really delved into the details of how that would actually work.
Okay.
And that's what I'd like to focus on in the final part of our deep dive.
Okay, I'm definitely ready to explore that.
Good.
We've seen how hydrogen isotopes can power stars, illuminate the dark,
Right.
and even unlock the secrets of life. Now, I'm curious to know how this seemingly simple element can help us create a more sustainable future for our planet.
It's a topic that's both fascinating and incredibly relevant to the challenges we face today.
Well, I can't wait to dive into that discussion. Join us for the final part of our hydrogen deep dive, where we'll explore the possibilities and challenges of using hydrogen as a clean energy source for a brighter tomorrow. Welcome back to the deep dive. We've explored the atomic quirks of hydrogen, its fascinating isotopes, and even ventured into the world of heavy water.
It's been quite a journey.
It has. Now it's time to tackle the big question.
Okay.
Can hydrogen truly fuel a cleaner future?
It's a question that's on the minds of a lot of people these days.
Yeah, for sure. Scientists, policymakers, and really anyone who's concerned about climate change.
Right.
So what's the answer?
Well, like most things in science, it's nuanced.
Okay.
Hydrogen definitely has immense potential,
Mm-hmm.
but there are definitely challenges we need to overcome.
Okay, so let's break it down. We've talked about hydrogen fuel cells,
Right.
but I'm guessing that's just one piece of the puzzle.
Yeah, fuel cells are just one application.
So what's the bigger picture when it
What?
comes to hydrogen and clean energy?
The broader vision is to use hydrogen as a versatile energy carrier.
A versatile energy carrier.
A way to store and transport energy from renewable sources,
Okay.
like solar and wind power.
So it's like a bridge between renewable energy generation and the various ways we use energy.
Exactly.
Cool.
Imagine a sunny day
Okay.
where solar panels are generating more electricity than we need at that moment.
Okay.
Instead of letting that excess energy go to waste,
Right.
we could use it to split water molecules
Uh,
through a process called electrolysis.
we talked about electrolysis earlier, right?
We did.
When we were discussing how nascent hydrogen is produced.
Right. So we're basically using electricity to create hydrogen gas from water.
So we're capturing renewable energy when it's abundant
Yeah.
and storing it in the form of hydrogen for later use.
Exactly.
That sounds incredibly efficient and sustainable.
It's a really elegant solution.
It is, and the beauty of hydrogen is its versatility,
Right.
like you were saying.
It can be used in a variety of ways, making it a flexible tool for decarbonizing different sectors of the economy.
Okay, I'm sold on the concept.
It's good.
But I'm sure there are hurdles to overcome before we all have hydrogen-powered cars and homes.
Of course.
What are the biggest challenges facing the hydrogen economy?
I think one of the most significant challenges is scaling up the production of what's known as green hydrogen.
Green hydrogen.
Yeah.
Is there a difference between regular hydrogen and green hydrogen?
There is. Currently, most hydrogen production relies on fossil fuels, which kind of defeats the purpose of clean energy.
Right.
Green hydrogen, on the other hand, is produced using renewable energy sources.
Okay.
So that ensures that the entire process is carbon neutral.
So it's not just about using hydrogen.
Right.
It's about producing it in a way that's truly sustainable.
Exactly, and that's where electrolysis comes in.
Okay.
If we can power electrolysis with renewable energy,
Yeah.
we can create a closed loop, a truly sustainable hydrogen ecosystem.
That makes a lot of sense. But what about the cost? Isn't producing green hydrogen still quite expensive?
It is currently more expensive than producing hydrogen from fossil fuels,
Okay.
but the costs are steadily decreasing as technology advances and economies of scale kick in.
Okay.
Governments and industries around the world are investing heavily in research and development to make green hydrogen more competitive.
So it's a matter of time and investment before green hydrogen becomes a viable alternative to fossil fuels.
That's the hope. And there are other challenges, too.
Like what?
We need to build the infrastructure
Uh-huh.
to transport and store hydrogen safely and efficiently.
Okay.
And we need to develop new technologies and applications
Right.
that make the most of hydrogen's unique properties.
It sounds like a complex undertaking,
It is.
but also an incredibly exciting one.
Absolutely.
It's like we're on the cusp of a new energy era.
Yeah.
One powered by this tiny but mighty element.
I agree. It is an exciting time.
It is. And while there's still work to be done, the potential benefits of a hydrogen-powered future are enormous.
They are. We could drastically reduce our reliance on fossil fuels,
Yeah.
mitigate climate change, and create a more sustainable and resilient energy system.
It's an inspiring vision.
Yeah.
This deep dive has really opened my eyes to the incredible possibilities of hydrogen.
I'm glad to hear that.
We started with this simple element that
Oh.
can't even decide where it belongs on the periodic table.
Right.
And now we're talking about powering the world with it.
It's pretty amazing.
Yeah.
It just goes to show that even the simplest things can hold immense potential.
Absolutely.
And it's a reminder that scientific exploration and innovation are key to solving the challenges we face as a society.
Well said. Well, that brings us to the end of our hydrogen deep dive. I hope you've enjoyed this journey into the atomic world as much as I have.
It's been a pleasure exploring this remarkable element with you.
And to our listeners, if you're curious to learn more about hydrogen and its role in shaping a sustainable future, there's a wealth of information out there. Don't be afraid to dive in and explore. Who knows, maybe you'll be the one to unlock the next breakthrough in hydrogen technology.
The future is full of possibilities. Thanks for joining us.